Welcome to the Getting Started tutorials of VirtualLab Fusion. In this session, we plan to deal with the following task. Given an input laser of 780 nanometer wavelength and beam diameter of 500 microns, the target is to couple the laser beam into a single-mode fiber with a mode field diameter of 4.9 microns. The situation described above is similar to the one given in the tutorial for a fiber coupling system with beam expanders. However, here we would like to have a compact system with a single coupling lens, which should realize an optimized coupling efficiency with a requirement not to use additional optics. Before searching for real lenses, let us first figure out what kinds of lenses are good for this job. To achieve a high coupling efficiency, the laser beam at the fiber end must fit to the mode of a fiber. For a given wavelength, beam diameter and mode field diameter of the fiber, the coupling lens should have a focal length according to this expression. Substituting the parameters of our particular case into the equation, we can calculate the focal length, obtaining a result of 2.467 mm. This result can be easily verified in VirtualLab by using an ideal lens. One may find both real and ideal components in VirtualLab. Ideal components do not have a geometrical and material description. They are merely represented by optical functions. This type of component is of great help for system analysis and design. Especially during the early stages of a design process, it is often beneficial to have a functional representation of the components as a first approximation. It goes without saying that these ideal components can of course work together with real ones in the same system. It is therefore possible to replace the idealized components step by step as the design process progresses. The ideal lens component may be found under Ideal Components, Apertures and Lenses. Add one into your LPD. In the Physical Parameters tab, we set the focal length of the lens equal to 2.467 mm. The next step is to add a Gaussian source into the LPD from Light Sources, Basic Source Models. This source is intended to represent the input laser beam, so we set the beam radius to 250 microns in both directions, so that a beam diameter of 500 microns is obtained. In the Spectral Parameters tab, modify the wavelength of a beam to coincide with the design wavelength at 780 nanometers. Finally, add a virtual screen at a distance of 2.467 mm behind the lens. As recommended, we run the simulation first with the Ray Tracing System Analyzer, which produces a 3D view of the rays in the system. The ideal lens is represented as a plane, and it coincides with a Gaussian wave, since the distance between the two is 0. Let us then switch from the 3D to the 2D view, which by default shows a dot diagram at the last plane in the system. In the case in hand, this corresponds to the focal plane, where we see a single dot even after zooming in. This is because the ideal lens converts a plane wavefront into a perfectly spherical one, with a radius of curvature equal to the focal distance of the lens. Therefore, all the rays departing from a spherical wavefront will converge to the center of the sphere. However, due to the fact that electromagnetic fields diffract, and this effect plays a dominant role in the focal region, a dot diagram from ray tracing cannot deliver a realistic physical picture near focus. We need to switch to a field tracing engine. But before running the simulation, let us make a few modifications to our light path diagram. First, place an identity operator from Ideal Components, Manipulators at the focus position by copying the Z coordinate value. Then delete the connection of the virtual screen by first selecting said connection and then pressing delete on the keyboard. Afterwards, connect the virtual screen to the identity operator with 0 distance in between. Finally, add a Fibre Coupling Efficiency detector. In the Detector Function tab, set the mode field diameter to 4.9 microns. Let us say a few words about the inclusion in our system of the identity operator. This component represents, as the name suggests, an identity operation, and as such does not change the field. It is a very useful element to include when multiple detectors are to be used in the same position, as it is enough to connect all such detectors to the identity operator and then only modify the coordinates of the latter. Now let's run the simulation. We obtain the focused Gaussian field, which is also employed for the complex overlap integral calculation in the fibre coupling efficiency detector. The coupling efficiency is thus computed and displayed in the Detector Results Information tab at the bottom of the screen. Since the ideal lens has exactly the desired focal length and it converts the input Gaussian beam almost perfectly to the fibre mode at the focus position, an efficiency of almost 100% is obtained. The next question is to find a real lens that fulfills the same coupling task with a high enough efficiency. A rough search of the Edmund Optics website provides two possible lenses, an aspherical lens with a code 64802 and a spherical one with code 65254. Both of them have an effective focal length of 2 mm, which differs from the desired value. A more thorough search could perhaps yield better lenses for our particular task, but generally, in practice, it is very common to encounter this kind of limitation, so we will work with these two lenses as an example. Let us start with a spherical lens. Edmund Optics provides a Zemax file of the lens on their website. Please download this file or find it included in the sample files for this tutorial. In what follows, we will directly import the Zemax file into VirtualLab for further analysis. This step requires a glass catalogue from Zemax. We suggest that you create a new light path diagram for this. To import the lens data, first add an optical interface sequence component into the LPD. Click on the Tools icon and select Import Zemax file, browse to the correct location and select the corresponding lens file. After the import, the preview shown at the top of the window may look a bit strange. This is because a Zemax file always contains two plane surfaces in front of and behind the actual optical lens. By examining the table of surfaces in detail, it is easy to see that there is a 1 meter thick airspace between the first plane interface and the spherical surface. Therefore, delete the first and last interfaces from the table. The actual geometry of the lens should then become visible. Add a Gaussian wave with 780 nanometer wavelength and 250 micron waist radius, as we did in the previous case with the ideal lens. Add a virtual screen. When it comes to positioning this screen, bear in mind that an effective focal length of 2 mm is not the same as the distance from the last surface of the lens and the focal position, so we use the Find Focus Position function in the light path ribbon to find the actual position of the focal spot. Now the time has come to check the system with a Ray Tracing System Analyzer. In the 2D view, the effect of the aberrations of the lens is obvious. The resulting dot diagram deviates a lot from a perfect dot in comparison with the case with the ideal lens. As before, we also want to include the Fibre Coupling Efficiency detector, so we add it alongside an identity operator and set up the system the same way as we did for the example with the ideal lens. With a field tracing engine, we obtain a measurement for the coupling efficiency of about 56% with the current choice of spherical lens. It is not very satisfactory. Is this caused by the fact that the focal length of a lens differs too much from the desired one? Before answering this question, let us check out the aspherical lens. The construction of the system with the aspherical lens should be analogous to the previous case, so we will therefore not repeat the process. During the import of the aspherical lens, however, one should pay attention to the following fact. After deleting the first and last interfaces from the lens surface table, we see that there is a 250 micron thick glass plate behind the lens, in addition to it. It is possibly a piece of protective glass. For a monochromatic laser operator, the glass plate does not influence system performance, so it is irrelevant to either keep it or delete it. We keep it in this example. The dot diagram at the focal plane shows a very uniform dot distribution, and the overall area covered by the diagram is much smaller in comparison with a spherical lens. Even before performing a quantitative analysis of results, it is easy to infer from this that there is a far better control of aberrations with the aspherical lens. Next, in order to analyze a coupling efficiency, we switch to field tracing and apply the Fibre Coupling Efficiency detector. With the aspherical lens, we get a coupling efficiency of around 95%, much higher than with a spherical lens, despite the fact that both lenses have the same effective focal length. What causes the difference? Let us examine the field in focus in both cases. Zoom in using the button in the view ribbon or by using the scrolling wheel on the mouse. The two fields will very possibly be scaled to different sizes, which makes it hard to perform a reliable comparison. For a quick visual check, VirtualLab provides the useful tool Copy View Settings. Activate one of the result windows by clicking on it. Here we choose the result of the spherical wave, and click on the Copy View Settings button in the view ribbon. From the pop-up, select the window from which the settings will be copied, in our case, the result of the aspherical lens. VirtualLab will automatically scale the view of the current window to match the selected one as closely as possible. Of course, the accuracy of this operation is limited by the finite sampling of both windows. Now it is possible to visually determine that in the case of the spherical lens, the field at the focus is much larger in size. This is mainly caused by the spherical aberration, which does not only modify the size of a field as explained, it also modulates the intensity profile. Both effects together amount to a poor coupling efficiency, as we have seen. With VirtualLab Fusion, it is possible to perform a full analysis of a complete system with either ideal or real components, which we hope can be helpful in your research work. If you have any questions, please don't hesitate to contact us.